So in this video series, I'm going to start building a NIXIE tube clock based on the B7971 tube. I've built several NIXIE clocks over the years, some my own design, some from kits, some kind of a hybrid of both. For my designs, I typically use a PIC microcontroller to kind of control the logic and those kind of things. Having essentially or recently acquired 6 of B7971s, these larger tubes, it's time to do a clock project again. 6 tubes will make a very nice large clock. These tubes are about 4.5 inches tall, as it indicates here. They're a nice large tube. I remember back when these tubes were pretty inexpensive, a decade plus ago, and now they're fairly difficult to find, and when they do sell, they're pretty expensive. I ended up with 2 very inexpensively. One of them cost me $1 at a surplus store. The other one was part of an estate sale where we bought basically bulk a lot of stuff, and there was a tube in that mix. These are a multi-segment tube. I believe it's 14 segments plus 15 for the underbar here. They can do alphanumerics. They're not as pretty, in my opinion, as a standard NIXIE tube where each one of the numbers is preformed and you get that nice glow. But you can do very cool things with these because you can do text, numbers, you know, I'll call it graphics, but little animations where segments go on and off. You know, I just think they're a really pretty tube. And now that I've got 6 of the B7971s, I decided it's time to move ahead. Initially, my thoughts were just to design the clock completely from scratch. And as I started to look online and explore, I realized in this case I'm really going to go ahead and use some pre-configured modules that just make it easy, and this will become more an assembly a video, and then I will do my own custom programming to control the system. The B7971 is kind of interesting in that there's different cathode currents called out depending on which segments you're talking to. This was done to keep uniform brightness on them. It creates, I'm not going to say a challenge, but you need a few different current limiting resistors. Just as a comment here, NIXIE tubes are really current driven. You need a high enough voltage to get the neon gas ionized. If you drive them with too much current, however, you'll get oxidization eventually and they'll dim. Actually, we can flip that around the other way around. If you drive them with too much current, you will boil tungsten off and actually get silvering deposit inside of the tube. On the flip side, if you're not driving them enough, they will then oxidize and get dimmer over time. So kind of paying attention to the typical drive currents and getting into that range is a good thing with NIXIE tubes. You know, we've got a comment here about individual cathode current for the various cathodes, the various segments, and you can see that it kind of jumps around. The total for all cathodes is about 21 milliamps with the tube fully lit. A lot of the little DC to DC converters, you know, it'll take 12 volts up to 170 or so, have about, you know, 20 to, I've seen a couple at 35 milliamps. Maximum current capacity, because I'd like to be able to light all segments potentially on all tubes. I'm going to have to take this into consideration. I will need probably multiple little DC to DC converters. I may end up doing 1 per tube. It seems a little overkill, but that would give me the ability to light all the segments on all the tubes if I wanted to. I will think about that a bit more. If I was driving 2 tubes, and again, you know, this is the max. That's you know 42 milliamps. You know, up here in the electrical characteristics for cathode current, total all cathodes, they're saying 12. I'm looking at the wrong tube here. I need to be looking at the 7971. I keep getting caught by that. We were looking at the right place here. You know, 21 milliamps at 170 volts. So I got to think about this a bit more. Anyhow, we've taken a quick peek at the data sheet here. You can, of course, find the data sheet online. I believe this is the Burroughs data sheet from back in the day. Anyhow, let's move on to look at kind of a presentation of what my overall design is going to be. Like I said, I originally started out thinking I was going to do all the drive electronics myself. And this just shifted into using these smart socket boards. I've kind of watched the development of them on and off over the years as I've, played with NIXIEs and then stepped away to do other things and back to NIXIEs. And the evolution of these smart socket boards has really been, pretty awesome. This board's designed to drive a B7971 tube. You've got the cathode switching transistors here where it'll take the cathode to ground, and that'll cause this, the individual segments to glow. In this case, we have 1, 2, 3, 4, 5, 6 segments lit to form that letter M. It's using a PIC microcontroller, so 5 volts out of the microcontroller through a 33 k ohm resistor will turn the transistor on, ground the cathode, that segment lights. The resistors around the outside edge here are the current limiting resistors, and there's values from 22K to 33K. I think it's 22, 24, 27, and 33K. And those values were picked to get the correct current flow for each one of the segments per basically what the data sheet says to do to get a more uniform brightness. Because I have 6 tubes, I'm going to use 6 smart sockets. Smart sockets are interesting in that you send a serial data stream to them. So on my main PIC microcontroller, I'll set up probably a software UART, or it might actually be a hardware UART if there's one in the PIC I choose. And essentially you're just sending ASCII characters out a serial port to the board. And the board's smart enough to, the first one to say, receive this data stream and say, oh, there's something to do. Oh, there's something, there's another character to be displayed. Send that first character out. And these just keep shifting the characters down. So if you sent 6 characters to be displayed, those would get shifted all the way through, and you'd have the first of the 6 character to be displayed. You then send a command that says display them. Those get latched, the proper segments light up. The ROM image for the smaller PIC microcontroller here has several fonts built in. It's got effects. It's actually pretty nice. I just didn't see the need to go off and develop my own software to do this when these are inexpensive. They're a pretty straightforward assembly. If you buy the blank boards, they're common parts. It just seemed like a good way to go here to get where I wanted to. This project's more about what I can make the clock do, and less about the engineering, although there'll be some engineering. I do plan to have a real-time clock chip on board, just for battery or time backup if the power's out. I also want to use a GPS module so I can look at the time from GPS satellites and have a very accurate time base. We talked about this being a serial bus. It's essentially, it is an RS-232 bus. The real-time clock uses an I2C bus to communicate with the PIC, and again, PICs have wonderful support for I2C. And the GPS modules I'm familiar with have a serial output as well, essentially an RS-232, a serial data stream, and you're receiving ASCII characters into the PIC that you're then parsing to pull the time and date out of. It gets a little interesting with GPS modules because you need to worry about daylight savings time on your own. And of course, these are on, I believe, GMT time, so you've got to translate forward or back to your local time. Again, that can all be done in software. There's going to need to be a couple of power supplies. There'll be the wall adapter here, which will produce 12 to 16 volts, whatever DC I plan to come in with. It'll need to have a 5 volt regulated output for each one of the microcontrollers up here, and these chips and devices down here, and that plus 170 volt DC supply that'll go to the anodes on each one of the tubes. As I said before, I may end up with 6 little DC to DC boost converters here to get my 170 volts. I may be able to share them. I'm considering an alternative design for this as well, as rather than using a wall adapter and these little switching converters, I actually do have a couple of NIXIE tube transformers, so transformers with a 180 volt tap, and I believe both of them have a 6.3 volt tap meant to drive the heaters and tubes. I I might be able to use one of those smaller transformers. I could certainly get the 170 volts at the current I need to drive all these. And with the 6.3 volt tap, with a low dropout regulator, I might be able to get a good solid 5 volt regulated rail for all the PIC controllers and the other hardware here with sufficient current. It's an alternative. The one advantage to that, I'm still debating it, is that if I've got a transformer in the design, I've got the AC, line coming in at 60 hertz here in North America, and on the output side of that, I can basically, what's the term I'm looking for? Use a zero crossing detector or some circuit to convert that 60 hertz smaller AC signal into 60 hertz pulses. And I could then, in that design, have a mode where you set the time and it's watching the incoming line frequency. And that incoming line frequency in the US is very stable. Over a day or two, it will average right on 60 hertz. It may move up and down a little bit during the day as the load on the generator stations change. But over long periods of time, that's a very stable 60 hertz source. And of course, in Europe, Russia, a lot of European countries in that part of the world, they have a 50 hertz line frequency, but you can do the same kind of thing. In one of my previous videos on a NIXIE tube clock I think I've posted that video some time ago, I talk about using the line frequency to actually drive the clock. These real-time clock modules rely on a 32 kilohertz crystal typically, and you do need to trim the capacitor on those in to get a very accurate over the long-term clock stability. If I was to use the line frequency to do this, I wouldn't have the GPS module necessarily. And it would only rely on the real-time clock chip if the power went out. So when the power would come on, it would get the current time from the chip and then use the AC line frequency to drive it. Like I say, these are design considerations I haven't gotten into. But for now, this is the plan to get me running. I use the MicroE development environment, MIKROE. For all my PIC development, I've got both their 16 and 32-bit development boards and software. I use the C compiler from them. I've had really good luck with it. I'm very comfortable with C. I think they do a really good job. They're a little spendy. The compiler's something over $200, and the development boards are I think $150, $200 range. But I've had really good luck with them. And they've got little boards that can plug onto those development boards that have an RTC chip. There's all kinds of little boards you can plug on. And they supply libraries. This could certainly be done with an Arduino. That would be another option. There's tons of libraries out there. But for me, I'm going to use the hardware I'm familiar with and most comfortable with, and that's the PIC series. This will probably be like an 18F or maybe a 16F series. One of the longer-term design goals in this is what's called the 4-letter word sculpture. It was first introduced, and I want to say Playboy magazine in the mid-1970s, and it used 15-segment NIXIE tubes as displays and a very simple at the time microcontroller, and it was able to generate random 4-letter words along with the time. And the algorithm that was used for the 4-letter words was really kind of interesting. It wasn't just a list of all 4-letter words and a lookup table. It was a little more sophisticated in that, partly driven by the lack of ROM in that controller. And I will in a later video get deeper into my implementation of that. Of course, with 6 digits, you could do 5-letter words, 6-letter words. You could do everything from 2-letter words to 6-letter words. The 4-letter word sculpture to me is kind of fun. Well, they all are, in that you can randomly turn on different letters as you expose the word. It's kind of fun to guess what it's going to be. It's always kind of fun when it comes up with a swear word, especially when you're not using a lookup table but you're essentially, just quickly to say it, using the distribution of letters in the English words, and then a random number generator or pseudo-random number generator to pick which ones to display where. It's a slick little algorithm. I've implemented it before in a couple of clocks. I really like it. I sadly no longer have all the design files from those. I'm going to have to start from scratch. Like I say, I'll get in a later video and detail all that. So anyhow, we've kind of looked over my thoughts on this, the approach I'm taking, some of the hardware I plan to use. We've talked about considerations for power supply. In this first video, we're going to kind of take a look at some of the bits and pieces. And like I said, this will be a multi-video series. I don't know how many it'll take to get this done. But, you know, we'll get there, and it should be a fun project. Well, after recently acquiring 6 of these B7971 15-segment NIXIE tubes, it's time to build something with them. And of course, my go-to is always a clock with anything NIXIE. And with 6 tubes, I can obviously do hours, minutes, and seconds, which I will certainly do. But I also think about the 4-letter word sculpture that was made in the 1970s that basically used an algorithm to generate random 4-letter words, and it was fascinating to watch. It's been re-implemented by a number of people. I plan to implement that as well. I started looking at what it was going to take to drive the tubes, because I thought I was going to design all the hardware myself, and I came across these smart sockets, and I've followed kind of the smart sockets on and off over the years, and decided, what the heck, I'm just going to go ahead and use smart sockets to do this. If you're not familiar with smart sockets, you can gang multiples together. They're communicated to via a serial data stream. So basically 5-volt level RS-232. You send the text you want displayed into the first board, it's daisy chained to the second and the third, and so on down the line. It uses a PIC microcontroller to control it. It's got fonts built in and fades and all the stuff that make it fun and interesting to watch. And rather than re-implement that all myself, I decided, what the heck, I'd go ahead and just purchase the boards. They were like $3 a board. Hit DigiKey, get all the parts I didn't have in stock, and solder the boards up. And then I will use these to actually drive the displays. I will still need, of course, the 170 volt power supply, capable of enough current to drive 6 of these tubes. They're 15 segments each, and I think they run between 1 and 2 milliamps a segment, if I remember right. I'm going to have to look at the data sheet, which means you're approaching 30 milliamps a tube. And 6 tubes, that's 120 milliamps. And most of the little universal, switching modules you can get on eBay are good for 20 or 30 milliamps. So I either have to do something different to power this, or potentially just use a number of those pre-made modules. Yeah, this is turning more and more into pre-made stuff. I will probably be using a PIC 16 series to drive the whole thing. I've got some 16F 450s or 460s here, I think. And I'll just develop the code in C. I want to put a GPS module on it to sync the time, those kinds of things. Anyhow, there'll be multiple videos in this series. Really, in this first video, I just wanted to take a quick look at the tubes. You've seen these lit up on the internet. I won't take the time to light these up. This one's from the 23rd week of 1958, potentially. Maybe 68. It's hard to say. It's an ultrasonic. Like I say, I've ended up with 6 of these guys. The pins on this one are rather messy. It's been pulled out of a socket crooked. I'm going to need to spend a bit of time and straighten pins. Pins need to be nice and square to the body so that there's the minimum stress going into a socket like this. If you're using the regular sockets the tubes come with, those pins float in there, and it's a little bit easier, a little more forgiving of the tube. Because these pins are soldered to the board, they're much stiffer, and so you really do want the pins nice and square and straight to minimize the amount of stress plugging it in and having it retained in the board. And of course, if you stress these too much, you can break the seal between the pin and the glass, and then the gas escapes from the tube, and the neon quits working and the tube fails. So It's worth the time to go into straighten pins, and this one's actually fairly bad. Like I said, I've ordered 6 of the little boards. I've got the assembly notes here for the boards, which has, you know, schematics, dimensions, part layout. There's apparently a couple of resistor substitutions, so the silk screen on the board was incorrect. I assume these boards probably have the same issue. Now this one's actually labeled 22K there and 24K there. So the silk screen has been updated on the boards I've got. That helps. Look through the board. There is, of course, the BOM. And then there's multiple pages that he's put together to kind of walk you through assembly. I'm hoping I've got some Kapton tape here. I used to have, because I will probably follow this method of actually getting the pins to the boards, and that's drop them in, Kapton tape them down, and solder them probably up against the work surface here, which will take the heat. Anyhow, kind of look through all of that. The last thing to do in this first little video is we kind of introduce what we're going to do here. Let's go ahead and open up the box from DigiKey and see what we've got. I didn't get the tape cut all the way to the end. There we go. It's always interesting with DigiKey. You get all kinds of interesting and weird shaped boxes from them. They must have like an infinite supply of oddly shaped boxes. You've got lots of bags of stuff. Let's kind of take a look at each of these. These pins are actually a lot smaller than I expected. They were the ones that were called out. On the website I downloaded the materials from. Let me just get one here. I did, as always, order a few extras. Almost impossible to physically hold on to. These big old hands of mine. Well, I am determined to drop it and lose it, that's for sure. It fits well on there. It's not super stiff, but it feels like it will make good electrical contact. I may want to burnish these pins a bit just to clean them up. There is some age oxidization on them. Nope, these pins should be just absolutely fine. So I ordered 100, I believe, of the little pins. 120 actually. It doesn't look like 120, but I'm going to assume they can count. And these are, of course, the little pins that go through these holes here for the socket to sit into. I went ahead and ordered 6 of these little connectors that'll mount down here on this bottom edge of the board. And they are screw type, and so I can just run wires between the boards to build a daisy chain for the serial and pass the power along. These are the high voltage transistors, of which you need a buku. I ordered 120 of them again, so I have 20 extra. These only came in tape, which I'm fine with. These are high voltage transistors. These are used to turn the segments on. Every segment and every tube has its own driver transistor. So as you can imagine, there's a lot of soldering there. And these should be the PIC microcontroller, since I didn't have enough of these in my stock. There should be, I think I ordered just exactly enough, 6. Yeah, 6 total. So these are PIC 16F690s. I've got it. Several PIC programmers will be able to program these up myself. There is an ISP connector here. You could potentially program them in circuit. I will socket these devices as well. You know, I'll program them on my standalone programmer, and then they'll be socketed to the board. The spiking caps and the resistors, I have all that kind of stuff in my stock here, so I didn't order those kind of common parts. But these were all things I didn't have in stock or have enough of in stock to be able to do this on my own. So, last thing I'm going to take a look at here, that's not the pliers I want. Although they may work. Just to take a look at straightening these pins. Again, I want to be very gentle here in doing this. They are really skewed. Somebody was not kind to this tube in its previous life. It doesn't look too bad. Board this way. The problem is it doesn't take much to really mess this up. These are greatly bent. This tube came from an estate sale. We did kind of a bulk purchase of a ton of stuff. It was one NIXIE tube in the materials we bought that I grabbed. I've got another one here that came from Electronics Recycler that I got for a whole $1. So miracle prices on tubes do happen. That tube has been tested, and I've watched this one run in the one tube clock it was originally in. And you know, the guy that built the one tube clock, at least I think it's a clock, it's really beautiful. The build, however, I cannot figure out how to set it, and what it displays makes absolutely no sense to me. It doesn't appear to be the time. She said something about it being a Y2K countdown timer, and kind of watching the weird stuff it does, that may be what it was. It uses a pretty standard NMOS clock chip, but at the same time, you know, it's flashing four numbers across it and pausing, so you're supposed to be, you know, taking that serialized set of 4 numbers in your head and getting them back as a string. And visually these pins are looking much better. It just doesn't make a lot of sense to me. See what it looks like through the board again. So I'm just kind of moving the board around, just kind of watching. You know, I can see, get a little bit of idea of what pins are the most out of alignment. And it's not too awful bad. Say the pin to glass interface is rather delicate, and if you break that seal, you'll lose the neon gas, the tube will fail, and at that point it is truly scrap. So anyhow, I will wrap this first little video up here. Like I said, this will be a series of videos, and the next video we'll probably assemble one of these little boards I will assemble one complete board first. Then we'll test it thoroughly before I assemble the others, in case I'm getting a component incorrect, or sourced the wrong transistors accidentally or something. So anyhow, that'll be coming up in a future video.